Good morning, Astronomy 1010. Welcome to our third lecture, part one. Today, you're going to be learning some classic astronomy stuff. You're going to be learning phases of the moon. We've got a little module on eclipses. We'll be teaching you a little bit about observational planetary periods, which are not the same as the time it takes a planet to go around the sun. And then we'll sort of transition into the history of astronomy and learn a little bit about Greek astronomy and what motivated philosophers like Plato and Aristotle to contemplate the cosmos as a geocentric universe where the Earth was the center of the heavens, and how that actually relates to observational things that we see in the sky. A couple of quick notes before we get into our lecture show. I actually did all my grading for once. I graded all your damn papers. I can't believe it. I got something done. Okay, so in the process, I've learned who's been naughty and who's been nice. And anyone who did not turn in any lab or homework to me was marked as a no-show, as I have to do verification of enrollment. So if you did not turn in any homework or lab, you would have been automatically dropped from the course by now. Now, I still kept your email on the list so that you could beg for mercy. And the usual thing that I do for anyone who has been dropped from the course is I make you catch up on everything that you should have turned in before I give you the opportunity to rejoin the course, which I think is fair. If you're going to say, oh, I'll catch up on that stuff, well, you got to prove it now, okay? For the rest of you, the danger is that if you got in some of your work, but not all of it, that you could start getting behind, and we don't want that to happen. Now, I spend the time hanging out with you, and I do this work with you. So all you have to do is hang out with me and follow the bouncing ball. That's not too much to ask for. So please do it, okay? Marissa or Ethan, people who are in the background there, if you owe me stuff, then just sit down today while it's snowy and cold outside and beast it out. And then we'll all be, I'll tell you, I felt wonderful after I caught up with my grading. So you're going to feel great after you catch up with your homeworks, okay? Okay, next up, John, can we change your names? I remember that you're John, but I know that's, let me do it. I think I can just rename you real simple. Is that acceptable to you?
That's cool.
All right, awesome. All right, let's take a look at some moon stuff, okay? Oh, by the way, I should mention that today's lab is a very cool lab on eclipse prediction. So what I think we should do is we should head on over to Lab tab, or at least I should, and let's right-click our eclipse prediction PDF. This is one where the actual, all of this background stuff, all of this, all of these pages can be somewhat helpful for this lab. But the two that I think we really need are this page, 1999 eclipse data, and this is our data sheet. Oh man, this is the older one that has, it wasn't scanned very well. You could see a person did a sloppy, crooked job. I thought I had a better version of this eclipse prediction lab. Let me see real quick if I can. Eclipse prediction improved. Aha. Okay, guys, here's what I want you to do. I want to send you all eclipse prediction improved, and then I want to swap this out. Sorry that we're doing this real time. I'm going to get printing on this now, but really the only pages that we need to print are here, print. There are 6 pages. The only pages you should actually need to print are pages 5 and 6. So pages 5 through 6. And the rest we can read the instructions from the PDF. Let me do 2 things. Let me go into the chat and let me share file. And I think that was in here. Oh, don't do this. Details. Boom. Okay, so I just sent that into the chat, so that's where you can grab it from. And for the students watching later on, I should really get rid of the old one, edit. Excuse me. This will just take a second, but I don't want to forget to do this, and I know I will. Come on. Blackboard is the worst. Here we go. Edit. And we will remove this file. Mark for removal. We will browse local files. We will get our labs, Eclipse prediction improved. Okay, that's what should have happened there. Oh, fuck. This is only for the night class, I think. Yeah. Okay, day people, I'll get to you in a minute. For now, just grab the one off the chat and see if you guys can remind me to do that for the other two. Okay. Okay, so let's go grab our lecture shows here. And what we want to do is we want to take a look at some classic stuff. I didn't really learn my phases of the moon until grad school, believe it or not. And it was a fellow grad student who taught me that you can make a simple little diagram and you can learn all of your moon phases. Can everyone see my slides here? All right. So we have 8 phases of the moon. And what we're going to do is we're going to do a little Bob Ross time together where I teach you how to draw a picture of this. Wait, someone's got some snap, crackle, pop there. Can you all mute yourself if you're not participating actively in the convo?
Sorry.
All right. Thank you. Okay. The Earth, the spinning Earth, is a clock. And an observer, which you can see here rotating counterclockwise as seen from north, their head is roughly in line with the meridian of their sky. Usually we like to imagine observers facing south. So let's here, come back to slide 81 or 82. We are going to imagine 68 that our observer is standing in the middle of a field. So here we go. Oh, let's grab red. So you are an observer standing here in the middle of a field. And we're going to imagine that you're looking south, okay? And you're watching the nighttime sky rotate around you. And objects like the moon will rise somewhere in the east, not always due east, somewhere in the east. It will come up and it will cross your meridian at its highest journey through your sky, and it will sink back down in the south. Basically, it takes a path very similar to that of the sun, which you learned all about in your last lecture. Now, things are going to get a little bit weird when we try to do a top-down point of view. Now, we're imagining the observer, we're looking from the North Pole of Earth in space, and we're watching the observer spinning counterclockwise. But I want to start by getting this idea correct, that this line over the observer's head is not exactly the zenith, though you could kind of think about it that way. You should think of this line over the observer's head as the meridian. And when the observer's meridian points in different directions, it's kind of like the hand of a clock, where when your meridian points towards the sun is on your meridian and it's noon. When your meridian points away from the sun, it's midnight, because the sun is at the lowest point that it could be in your sky. And we're going to make a diagram that starts off looking something like this. So let's go ahead and do that. Label this module Phases of the Moon. Let's leave ourselves a lot of headroom. I could really use a good circle maker here. That's another thing I meant to grab. A coffee lid would be perfect for me if I only had something like that. Okay. Start off by drawing a circular Earth in the center of the frame. And the first thing that we have to do is we have to choose the direction from which the sunlight is coming. And I always choose the sunlight to come from the right-hand side because that's my bias, okay? Very important that you guys pay attention to which direction the sunlight is coming from. Let's label over here to the sun, all right? The book's diagram is not so great. Ours should actually be better. The first thing that we're going to do is we're going to draw the boundary between the daytime and the nighttime side of Earth. So let's draw a vertical line. In astronomy, this line is known as the terminator, okay? And the terminator is the boundary between daytime and nighttime on your planet or your moon. So let's go ahead and let's shade. Obviously, the nighttime side of Earth will be the side that's opposite the sunlight. So we're shading in the nighttime side of Earth here because no sunlight is reaching that part of the sphere. The spinning Earth spins counterclockwise as seen from north. And as I mentioned, an observer who's standing on this spinning sphere will rotate through a 24-hour day, and the rotation of the sky is a clock. When your meridian points towards the sun, that's 12 p.m. If it points away from the sun, 12 a.m. When your head rotates 90 degrees with respect to the sun will be on your western horizon. Never forget that counterclockwise is east. So that spin is east, that spin is west. That makes this 6 p.m., 6 a.m. If you really want, you could even throw in some other times too. You could do 9 a.m., 3 p.m., 9 p.m., 3 a.m. All right. What we're going to do next is we're going to draw a number of moons. Maybe the inside of this would be nice. I'm going to draw 8 moons. First, I'll start with a cross. And then I'll put the moons in between the cross as well. So there should be 8 phases of the moon. A quarter might make a nice thing to use as a circle maker if you don't have one. Quarter, something like that. All right. So here are 8 phases of the moon, and we're going to draw in the terminator for each one of those phases. So draw a vertical line for each and every moon. You can use a straight edge. That will greatly improve your diagram, I promise you. Okay. Let's shade in the nighttime sides of the moon. The moon also has a daytime and a nighttime side. We've just drawn in the terminators. So I'll shade in the dark side of the moon, or the nighttime side of the moon, always pointed away from the sun. All right. Now, if you could fly high above the orbit of the Earth and Moon, this is what the moon's phases would look like. Let's keep a few things in mind before we start talking about this. The Earth spins on its axis in 1 day or 24 hours. But do you guys know how long it takes the moon to go around the Earth? Someone wrote me an email about that the other day. Take a guess. How long roughly does it take the moon to go around Earth?
28 days.
Pardon?
Is it 28 days?
Mm, close to it, yeah. It's 27 and a half, but yeah, 28 is a close approximation. It turns out that there are two periods of the moon. There's the time it takes to go around Earth, and then there's the time it takes to complete a set of phases. I will teach you about that after we do eclipses. It's hard to teach you that until you've kind of learned your phases of the moon. Okay. This is what the moon's, oh, by the way, the point that I'm trying to make is the moon's orbit is close to a month. So on a single day, the moon will not move that much through its orbit. It does a little bit, but for the most part, for now, you should just think of yourself as each day, the moon will stick in one of these positions and Earth will spin in a 24-hour day. And then about 3 or 4 days later, the moon will shift to a new position. Earth will spin around again 24 hours. So think of the moon as fixed day by day and the Earth is spinning underneath it. Let's label the moons, and then we'll talk about how we get the phases that we're familiar with when we look up at the nighttime sky. The moon in between Earth and the sun is the new moon. The moon opposite the sun is the full moon. As we go, and the moon's also orbiting counterclockwise around Earth, right? So everything is spinning eastward or counterclockwise. As the moon goes from new to full, it will grow. The disk will grow in our sky, and that means it's waxing. Waxing means to grow or to increase. So this phase is waxing crescent. This phase is called first quarter. This is waxing gibbous. And then from full to new, the moon is going to be shrinking. The disk will be shrinking in our sky. So this is, shrinking means to wane or to decrease. So this will be waning gibbous. This is third quarter. Sometimes they call it last quarter, but third quarter is more common. And then this is waning crescent. Take note that the crescent moons are the ones next to the new moon. The gibbous moons are the ones next to the full moon. All right. Now you've got your names of the moon. Now here I usually have a moon globe. Darn, I'm going to be missing that today. I have a moon globe that I do not have with me here today. I wonder if I could try to use this Earth globe. Might not be the same thing. Huh. I really need to go to CCRI and get some of my tools, my demos and such. Okay. The moon is a spherical body, right? But you're looking at it from so far away that the moon's spherical nature is flattened as a disk, but the curvature still affects the geometry. You should think of the moon as having this belly, this protuberant belly that sticks out towards Earth. When you illuminate a slice of the moon, you are illuminating something that's essentially like a tangerine slice. But when it gets flattened onto the sky, that gives it some curvature. And to understand how that curvature develops, remember that if you're standing at some location, like for instance, at 12 p.m., that's when the new moon is highest in your sky. That's when the new moon crosses your meridian. Notice an observer whose meridian points to 12 p.m. is only going to see the side of the moon that's facing Earth, which is the dark side. So when it's time to observe the new moon, you don't see anything for two reasons. One, you're looking at the dark side of the moon, and two, it's up during the day. And that makes it impossible to see any aspect of the moon. So the new moon is missing from the sky. For the first quarter moon, you're going to see a 2D cross section where half of the disk is in darkness and half of the disk is illuminated. So if you don't already know this, the first quarter moon looks like a half of a disk, right? You see half a moon illuminated in your sky. For the waning crescent moon, you're seeing a two-dimensional cross section that looks like that, where there's kind of like this pizza slice that is illuminated. And here's where the three-dimensional nature of the moon comes into play. A pizza slice is actually a three-dimensional tangerine slice, and that's going to end up flattened on your sky, and it's going to look like a fingernail, okay? So that's what they call it in the Arabian Nights. When the moon is a sliver, they call it the fingernail moon, and that's a crescent moon. Let's see if I can draw that. My art skills are not really good. That's why I made a better science student. Let's see, one more time. Yeah. Okay. So there's your crescent moon. You're seeing a 3D slice, and when it's flattened on the sky, the curvature becomes part of a fingernail. Same thing with the waxing gibbous moon. The gibbous moon kind of looks like an egg. There's a slice that's in darkness, and the rest of the disk is illuminated, right? So here the fingernail is dark, and the illuminated portion is kind of like an egg shape. So looks something like that, all right? The full moon, of course, you're going to see the full disk of the moon is illuminated. So the full moon, you can see that section of the moon that's bright, and then on it goes, right? So for waning gibbous, you see an egg shape. For third quarter, you see half an illuminated moon on your sky, and for waning crescent, once again, you're going to see a fingernail in the sky. Of course, you're seeing it from upside down, so the horns kind of point in the other direction. So because my art skills aren't super snappy, I've got a nice diagram here. Okay, so these are the phases as we first drew them. And oh, I guess earlier you can see the familiar shapes that you're used to in the sky. Now, the diagram that we made is actually a tool that we can use to predict and to understand the rise times and the set times of the moon. And here's how that's going to work. Let's imagine that as the Earth spins, our meridian, here I'm going to use blue for the meridian, our meridian will point towards the direction of our head, sort of, but the horizon line will be perpendicular to that. Okay, where the horizon that's spinning in this direction, this would be your eastern horizon, right? And this would be your western horizon. And it's twisting up like so. And as this thing spins, I wonder if I can't make this thing spin, can I? Here's where I make it difficult. I need to make this whole damned thing rotate so that we can watch the moon rise and set. Here, I might be able to better do this on the board. So let's put my marker as the observer's head, and we'll use this ruler. I don't think I have anything shorter, so I'm going to have to use this ruler. This ruler will be my horizon line. And as Earth spins, we can see moons rising above our eastern horizon here, crossing our meridian, and then the moon sets in the local sky when it dips below my western horizon, all right? Let's see if anyone understands me, which I'm not 100% sure I've made myself clear. Let's start with the new moon. Can someone tell me what time the new moon crosses the meridian of a local observer? What time does the new moon cross an observer's meridian?
Noon.
Right. Because when it's noon, your head is pointing in this direction towards both the moon and the sun. Let's try to use blue for that. What time would the new moon rise?
That I don't know.
Does anyone know?
Would it be around 6 or 9 a.m.?
Which one? Also, that's ambiguous because you didn't say AM or PM. Right? I don't know if you mean
Right.
AM or PM.
I said a.m.
Oh, I thought you said 6 or 9. Did you say 6 AM?
Yes, I said like, yeah, it was like 6 or 9 and then a.m. with a question mark.
Okay, you're pretty close. Yeah, it would actually be 6 AM. Let's see why it's 6 AM. When your meridian points in the direction of 6 AM, your horizon line is perpendicular to that, right? And this is your eastern horizon because it's spinning counterclockwise, like so, right? So here you can see the moon coming up in your local sky. What time does the new moon set then?
6 p.m.
That's right, 6 p.m. And you can see that here. If I spin here with my ruler, at 6 a.m., it will come up above my eastern horizon, cross my meridian at noon. At 6 p.m. it sets. In a way, that means that the new moon is up all day, right? May I erase this diagram? Does everyone sufficiently have that? Okay. Let's take these as notes. They will come in handy during your lab today on eclipse prediction, and they will come in handy during the exams and other times. So if we take the new moon will rise at 6 a.m. Your meridian, it crosses at noon, and it will set at 6 p.m. The new moon is up all day. Next, let's try the full moon. We want to be able to predict when it will rise, when it will cross our meridian, and when it will set. And our diagram should help us do that. So Daniel understood me. Can any of the rest of you, William, Ethan, Cole, Marissa, John? Ethan McGovern?
So the next one's going to be full moon.
Yeah. We've got a lovely shot of your ceiling. I can just see your head floating there.
Sadly, I do not have a great camera angle.
Oh, that's good. Were you the one who said your camera was embedded inside of your keyboard? Someone was telling me that they had...
No, that's me.
Oh, who the fuck puts a camera in a keyboard? That's crazy.
I have no idea. I actually ordered one, so we'll probably have videos soon. I ordered a new webcam because I'm gonna need it.
Absolutely. It's a requirement these days.
No,
Okay.
I just don't have a camera on my computer.
That's all right. Ethan, I'm not, that's the least of our worries. Can you predict what time the full moon will rise, set, or cross a person's meridian?
It will rise midnight.
No. At midnight, it
Oh, wait.
crosses.
Yeah,
Meridian.
6 p.m.
That's right. So at midnight, it crosses your meridian. When your meridian points at 6 p.m., that makes that will make this your eastern horizon, right?
Yeah.
Okay. So 6 p.m. it rises. Midnight it crosses your meridian. When does it set?
6 a.m.
That's right. So let's write that down. 6 p.m., 12 a.m., 6 a.m. The full moon is up all night. That's how I remember it. How about the first quarter moon? What time does so this should start to get easier if you're understanding what's going on. Cole?
It'll rise at noon.
Yep. Meridian Crossing?
6 a.m.
Not 6 a.m. because Earth is spinning like so, right?
Oh, yeah.
So if your head points like noon, this is your eastern horizon, right?
Yeah.
And then as it swings around, it'll cross your meridian at, try again?
6 p.m. 6
Yeah,
p.m.
6 p.m., the one that's underneath it, right?
Yeah.
And then when will it set?
It'll set at 6 a.m. then.
No, it rose at noon,
Oh, rose at noon.
crosses your meridian at 6 p.m.
Oh, midnight then?
Yes, midnight. So, oh shoot, I lost my diagram. It's hard to rotate the drawing there. So, right, because when your head points, I'll try to just do when your head.
Duration of time are we using to get these answers?
I'm sorry, say that again. Ask that question.
What duration of time are we using?
Well, duration of time. How do I answer that? We know that we can always see 1/2 of the celestial sphere from a previous lecture.
Does it change?
That fact does not change. You always see 1/2 of the celestial sphere in your local sky.
So,
So
it'll
just
be one duration of time for each phase of the moon as we see it pass through a meridian.
okay, all right. So okay, hold on. For now, it's more helpful for you to think of the moon being up in the sky for the same length of time. It does turn out that, like the sun, the moon can be up in your sky for slightly longer or slightly shorter, depending on what its declination is and where in its orbital path where along the ecliptic it's on.
How do we
But
guess that?
Huh?
How do we guess that?
Oh, we guess that because you can always see how. So I think the thing that you're missing is that you can always see 1/2 of the celestial sphere in your local sky. So why don't
No,
you watch?
I'm wondering why we're guessing that. What's the duration of time? Like 12 hours?
Uh,
Yeah. Okay. Thank you.
hold on, wait. Noon to noon. Yes. Yes, 12 hours, half a day. Half a day. Okay, look at it this way. Whoever I was talking to, do you agree that the Earth spins once in 24 hours? Do we agree on that? Who was I just talking to? I'm so confused, guys. Can you not do this to me? Who was I just having a dialogue with there? All right. Jesus. Okay, well, to try to answer whoever that person's question was, who I couldn't see, let me say that the reason why it's 12 hours is because if you spin 24 in a day, then your local sky is half of the globe, right? So a rotation through your local sky will be roughly 12 hours because it's half an Earth spin. In fact, the angle, the altitude of the moon can affect that. So remember that the moon's not perfectly on the orbital path of the ecliptic. So if we go back to that slide that I was at earlier, 61, the truth is the moon's length of time in the sky will depend on whether the moon was sort of below the ecliptic plane and has got a shallower cut through the sky, or the moon could have a higher cut through the sky by being north of the ecliptic plane, or it depends which orientation the ecliptic has. That's actually a quite difficult thing to see. If we look at another picture here, I shouldn't try to confuse you guys more than you're already going to be. I just need a picture of the ecliptic relative to Earth.
Does that mean that we can assume that with your declination of the moon being in the sky for longer periods of time than other days, that would be the reason that specific months have more days to them?
No, the number of the number of days in a month are actually an artifact of the Gregorian calendar. And historically, people had a difficult time figuring out how to make the cycle of the moon fit into a 365.25 day year. And so the Gregorian calendar, which we should talk about that sort of timekeeping at some point, was an attempt to regulate the number of days in a month so that they could keep putting the spring equinox would stay pegged to March 21st. In fact, the amount of time it takes the moon to go through a full set of phases is consistently 29.5 days. Our homework on Wednesday will explore this fact. So the time it takes to go through phases is 29.5 days. The time it takes for the moon to go around Earth is consistently 27.5 days. There's a synodic period and a sidereal period, and some diagrams in a few moments will help with that. In any case, what can be tricky here is that while your celestial equator always has the same arc through your local sky, the ecliptic does not. And you can see that the ecliptic is inclined to the celestial equator by 23.5 degrees. So sometimes when your sky cuts this way, the ecliptic can seem north of the celestial equator. Sometimes when your sky cuts in the other direction, the ecliptic can seem south of the celestial equator. And over here, it can seem aligned with it. And so it depends on the time of day and the time of year. It's quite complicated. That's unfortunate. That's because the ecliptic is with reference to the solar system rather than with reference to Earth. Let's try one more example just to make sure that we understand how the time thing is working. All right. So let's look at our phases of the moon diagram again. Let's say it's 3 in the morning and you're drunk and you're leaving the bar after it closes. They're finally kicking you out, okay? And you look to the east and you can see a crescent moon rising in the east. Is that a waning crescent moon or a waxing crescent moon?
Waxing.
No. Waning crescent, Cole. Cole, let's see why. If it's 3 a.m., your meridian in your head is pointing in that direction. Are we cool on that point? Okay. That means your horizon, which now I'll draw inconsistently in blue, your horizon points in that direction. And do you agree with me that this is your local sky? Because that's the direction your head's pointing. So all of this is the part of the sky that you can't see. You could never see a waxing crescent moon at 3 a.m. because it's basically at your nadir. It's underneath your horizon. The moon that you see rising in the east is the waning crescent moon. A good rule of thumb, Cole, to remember this is the waning crescent moon is the one that you see when you're up too early or maybe up too late. You know, you see the waning crescent moon at breakfast time or at dawn. When you see a crescent moon when you're, going home at night after your day job or something, or maybe after a day of classes, the crescent moon that you see around dinner time, around 3 to 6 p.m. is always the waxing crescent, okay? So if you practice using this little diagram, and remember, we made this diagram right in our notebooks, so you can use this diagram to figure out what the phase of the moon is. And a cute little, I encourage you guys to sort of keep track of this. When you see the moon in the sky at night, when you see it in a phase, challenge yourself to figure it out. Be like, wait, what phase of the moon is that? Do I recognize it? And like, for instance, tonight, if we were, actually, what is the phase of the moon tonight? It was full not too long ago, right? Ooh, I have this, you know what? I'm going to show you guys something cool.
Can you explain the moon in daytime?
Yeah, I will do that. So You can see the moon during the day, but a portion of it needs to be illuminated. So for instance, if you look here at the waxing crescent moon, you can see that the waxing crescent moon crosses your meridian at 3 p.m. And that's daytime, right? The moon shines by reflected sunlight, not by its own light. The reflected light from the moon is bright enough to punch through the blue sky. Of course, during a new moon, it's not possible because no portion of the illuminated moon is shining towards Earth. You're fighting against the blue sky and you're seeing the dark side of the moon. But as you guys know, not only can you see the moon during the day when it's, say, gibbous or first quarter, but sometimes even around dusk or something, you can even see the dark side of the moon. Here's a picture that I can show you. Here we go. Let's look at waxing crescent moon. Sorry, am I sharing my screen with you guys? I don't think I am. Let's try that, share screen. There's a picture that I'm looking for here. Let's see if I can find it. Have you guys ever seen something like this? This is pretty good. Sometimes when you look at the moon on your sky, not only can you see the oh, get the hell out of here. Oh, cool. Not only can you, screw you, Forbes.com. All right, let's try this again somehow. I know there's a good picture of it. Here, I think I like this one. Sometimes not only can you see the illuminated portion of the moon, but you can even see the dark side of the moon, the side of the moon that's not illuminated. Does anyone know how that is possible? How is it that you can sometimes see the outline of the disk and you can see this unilluminated portion of the moon? Anyone know what the deal is there? Well, this is what the Germans call the Gegenschein, the against light, okay? The moon, the illuminated moon, is bright in your nighttime sky. And if you've ever gone camping on a full moon, you know that the full moon in a forest is bright enough to actually cast a shadow on the forest floor. The moon has what angular size? Do you guys remember what the angular size of the moon is on our sky? Someone has to know the angular size of the moon. I am going to test you on this. This is going to be a test question. I'm not even trying to hide it from you. So it would be such a good idea for us to remember the angular size of the moon. Anyone?
I could be completely wrong, but is it 0.5
0.5 what?
degree?
That's right. It's half a degree on your sky. And the radius of the moon is, okay, it's 1,700 kilometers. The diameter is like 3,400 kilometers. What if we tried to imagine seeing the Earth from the moon's surface? Did you know that the Earth also goes through a set of phases just like the moon does? First of all, let's consider this. The radius of Earth is 6,400 kilometers. So I can't draw with the freaking mouse. In a rough and ready way, if we say the moon is 2,000 kilometers and the Earth is 6,000 kilometers, that means the Earth is about 3 times bigger. So the Earth in the sky of the moon should be about 1.5 degrees, which would seem totally insane if you were standing on the moon. It would seem really big and really bright. And meanwhile, the Earth is going through a full set of phases just like the moon. For instance, if you are here, if it's 9 p.m. and the waxing gibbous moon is crossing your meridian, an observer like Neil Armstrong, who is standing on the moon looking back at Earth, what phase of Earth do you think they would be seeing? If there's a waxing gibbous moon in your sky, what phase would the Earth be in as seen from the moon? Sorry?
Would it be a crescent?
What type of crescent?
Waning.
Waning, because it's exactly the opposite. In other words, a cut through the moon here, waning crescent, is the same cut through the illuminated portion of the Earth that you see here. But now imagine this. Imagine it's new moon, and you're looking back and seeing a full Earth in your sky. Can you imagine how bright the Earth must be from the surface of the moon? If its angular size is 1.5 degrees, it would seem absolutely massive. In fact, the Apollo astronauts who first photographed this were so startled by the appearance of the Earth on the horizon that they took a photograph of this during one of the Apollo missions when they were photographing craters on the moon. They took this legendary photograph known as Earthrise, and Earthrise has now become a sort of iconic, you can even get it on tights, it's so iconic, okay? An iconic image in astronomy. And here's a picture of it. Geez, I would love to not have an ad here and just have a picture of the thing. Yeah. So they snapped a photograph of Earth rising above the horizon on the moon. And this is considered a watershed moment in the history of humanity. Actually, the beginning of the environmental science movement, when people began taking measurements and studies of climate change, were actually pegged to the publication of this photo, I think in the 70s. Can you guys tell what phase the Earth is in right now, or at least what the shape is here? What shape is that? Based on the lectures we just had, what's the phase of the moon, of the Earth? Sorry.
Is it a gibbous moon?
Yeah, it's some type of a gibbous moon. So here you see Earth in gibbous phase rising above the horizon. And that's a lot of light. That's a lot of Earth light bouncing on the moon. This was considered an important moment in the history of astronomy. It was the first time people ever saw their planet sort of rising above an alien terrain or an alien horizon. And it gave people a sense of how connected and how small this little spaceship our Earth is. If you think about how this relates to the Gegenschein, that Earth light is so bright that it bounces off the unilluminated portion of the moon, and then it can bounce back to your eye on Earth. So when you can see the unilluminated portion of the moon on your sky, you're actually seeing the glow of Earth on the nighttime side of the moon. And that's wild. There's enough Earth light to bounce back and see it. Usually you can only see it during a crescent phase. And that's just because you get a lot of Gegenschein and you don't get too much moonlight, which will, drown it out. So the crescent moon's the best time to see the Gegenschein. Okay. Now that we've had that discussion, we can move into a discussion on eclipses. Oh, one last thing that I wanted to show you guys, kind of a show and tell here. I got this lovely gift from the girlfriend, and just a couple of days ago, this is an Alex Thibodeau 2022 lunar calendar. Let me go to full screen here because this is such a beautiful item. And he makes these absolutely beautiful, screen printed prints of the lunar phases for the year. And I want you guys to take a notice at what's going on here. So there's close to 30 days in a month, but not all months have 30 days, right? So January is 31, February can have anywhere from 28 or 29, depending on if it's a leap year. March is 31. And what you can see is the cycles of the phases of the moon not perfectly synced up to a month. Now, it might be hard to see, but what he's got for the full moons is he's got these kind of little blinky lights around it. It might be easier to see with the new moon, which is represented as, sorry guys, I'm all backwards on this thing, is represented as a bunch of empty circles. And what you can see is because the phases of the moon are 29.5 days, you can see the new moon each month drifting by almost a day. So it drifts by a day and then it keeps the same day and then it drifts back, but it's kind of constantly drifting backwards by about a day or so because the phases of the moon, the average number of days in a month is 30. But if the phases of the moon cycle every 29.5, they keep losing half a day and they keep drifting backwards with respect to the months of the year. So the cycle of the moon is only loosely bound to the days of a month. Lunar calendars are cool like that. Okay, it looks to me like every time there is a new moon, that the moon should be in between Earth and the sun, which it is. Why don't I get a solar eclipse?
Sorry, I have a question.
I'd love to hear your question.
So in the beginning of the lecture, you asked how long does the moon take to go around the Earth? And I said 28 days, so it's like 27.5. But you just said something about 29.5 days. And I'm like,
Yes.
wait, what? I'm confused.
Okay, let's do that one first. That's a lecture we wanted to have today. I was going to do eclipses first, but since you're curious, I think we should address that question right away. Let's take a quick module here. Let's talk about lunar phases or lunar time periods. There are 2 periods for the moon. And they're both related to a month. There is something called the sidereal month. The sidereal month is the true 360-degree orbit of the moon around Earth. And the sidereal month has a length of time which is, I actually think it's 27.3 days. I think that's what it is. The sidereal month is 27. Let's see here. I should have that memorized. What's wrong with me? 27.25 days. Oh yeah, here we go. 27.3 days. I was right. Then there's another orbital period called the Synodic month. The Synodic month is the time for the moon to cycle through its phases. In other words, a synodic month is the time to either go from new moon back to new moon or from full moon to full moon. I think we usually go new to new is how it's traditionally done. The word synod in Latin is Latin for meeting, like a meeting point. The synodic month, the time for the phases, is 29.5 days. So this is what you were getting confused about, my friend who asked me that question. This is not an obvious thing that there are 2 types of month. And I was bandying both about because I'm conversant with them, but this will be a little weird your first time around. To help you understand why there's a difference, why don't we take a look at a quick diagram here. Let's go to my astrometry lecture. And this is something I wanted to get to last class, but there just wasn't enough time.
Can you put the synodic month back up on the screen?
You mean the definition from my chalkboard? Yes.
Whatever you wrote down for the synodic month.
Sure. Take a second. Was that enough, or you got that?
We'll go through it. Using 29.
Whoever's, just let me know when you're done so I can go back to the slide.
New to new.
Is that cool?
Oh no, that's yeah, no, it's all good. No, don't wait on me.
All right, hold on. All right, okay. So let's go back to my slideshow here. F5, slide 6.
On by his definition.
Can we all see this? All right. Can you guys tell me, based on the lecture that you just had, what's the phase of the moon here in that configuration?
Waning crescent?
It's right up
No.
there.
Oh wait, no, that's a new moon.
That's a new moon. Okay, you corrected yourself. Was that you, Ethan? How did you
Yeah.
figure out that that was new? Explain that to the humans.
So I first looked at it, and my first thought was that it was in the spot that the
Yep.
waning crescent was.
I knew that was going to happen. Yep.
And I looked at it, and the moon is between the sun and the earth. And
That's what
where
matters. That's what
new
matters.
moon
Right
was.
now, that's right. The moon is between Earth and the sun. That's what makes it new relative to us. Now, Ethan, watch this. During the course of a month, the moon is orbiting Earth, and Earth is also sliding along the ecliptic by about a 30-degree angle. 1 month later, one sidereal month, you can clearly see that the moon has completed a 360-degree orbit because it's back to the same sort of configuration down here. But notice that it is not back to new moon. In fact, Ethan, considering that that's the Earth sun line, what is the phase of the moon there?
Orbit has it going in a counter.
now it's a waning crescent.
That's right. Now it's a waning crescent. In order to get back to new moon, you've got to rotate an extra 3 days or so to get them back into alignment. Now think about it. We are essentially no different than the Greek philosophers who were observing the moon from the ground. Most of us are not Neil Armstrong. Most of us do not get to fly around in our flying saucer. Wait, how the, I did a thing, guys. I put myself, okay, there we go. Most of us don't have the luxury of flying above the solar system in a flying saucer to watch the moon go around Earth. From our point of view, it seems like the moon has completed a orbit in the sky when it goes back to full moon or when it goes back to new moon, because we're not conscious of that sidereal aspect, right? Okay, so in other words, let me use some more adult language here. The synodic month is what an astronomer would call.
Explain it more. I don't get that. I don't get that part.
Okay, well, then talk to me. So are you saying that I did not sufficient, that you don't feel good about these two things? Can I do better? I want to do better. I don't know. Is someone talking to me, or are they just talking to their buddy in the background? I'm really confused, guys. Like, help me deal with the Zoom life here. Preston, is that you, Preston?
Oh my gosh, man, my mute has been like I don't know how long.
Preston, why don't you
Wow.
just fucking talk to me, man? I'm a human
I
being.
mean, I'm talking along, I think.
You certainly are. I'm listening to your inner monologue. Okay, we all are actually.
Yeah, that's something, isn't it? That's great.
Okay.
Yeah, all for the recording too. Make sure that gets up to YouTube. That's awesome.
I just wanted to know that was Preston. Okay, Preston.
Tag my link, you know. Subscribe to the channel. Sorry about that.
Honestly, that's okay. We should. I was actually looking for you to mute you, but I was talking at the same time, and it was distracting the hell out of me. Preston, it's okay if that's confusing. But because it is confusing, but you have to try to unconfuse yourself by thinking real hard about this. And the way that you unconfuse yourself, Preston, is you have to really have some things down. Did you see how it took Ethan a minute to figure out that this was the new phase? I expected that to take a minute because he was just kind of thinking about the diagram at first. And then he had to realize, no, it's about the sun-earth line. Where is the moon? That's why I told you guys what's so important is what direction the sunlight is coming from. If the sunlight is coming from here, new moon is when the moon is in between Earth and the sun. But you can see that the moon's going around Earth, and when it comes back around to the same spot here, it has completed a real orbit in the physics sense, we think of the period as being time to go around the Earth, right? It's completed a full 360-degree rotation because it's kind of back to the 4 o'clock hand on a clock, right? But it actually isn't back to new because it's not in between the Earth-Sun line. The moon's got to rotate an extra 30 degrees, which takes 2 to 3 days to get back to new phase. And this is a problem we have with many astronomical bodies. There's the orbital period that you see on your sky, the time it takes to orbit the sky and come back into alignment. But then there's the true orbital period around the sun or around the Earth in a heliocentric Copernican system. And those two things have to be calculated. In fact, there's a formula for it, which I will explain in just a moment.
So when it comes to guesstimate, oh, sorry, bro, I did not mean to interrupt you. I had
That's-
my mute off again, but I was looking to jump the gun on this one. So
Preston, talk.
the celestial sphere idea, as far as it being or pertaining to only the sidereal month, then that's going to be within a full orbit period, but it's not going to be to a new moon unless it goes through its synodic or.
That's
yes,
right.
Okay.
That's right. And this is why I was going to share some adult astronomy language with you. In
I
the
was just making sure I
astronomer,
got the
in
lingo.
the astronomer parlance, the synodic moon is, okay, I spelled that wrong. The synodic moon is the observable because that's what a observer on the ground can easily measure. We call the synodic month the observable because if you're a pig farmer in ancient Rome, you can look up at the sky and you can say it's full moon, and then you can count the days until the next full moon, and you would count 29.5 days. But now imagine that you're a pig farmer in ancient Rome. It would be quite difficult for you to know the sidereal month. You can't fly into outer space and watch the moon go around the Earth. You'd have to trust some astronomer person like me to tell you that that's what was going on. And that even might be a tough sell, but I know what the period of the moon is. It's the time I see, right? But this is the physics thing of what's the real orbit around Earth. I will come back to this in a minute, and there's a formula to calculate one from the other. We used it in our homeworks last week. I want to get to eclipses before we get out of hand here. And to understand how eclipses work, let's take note that the orbit of the moon is inclined 5 degrees with, that's okay, Preston, we're all cool with that. If anything, it was a helpful discussion. The orbit of the moon is inclined by 5 degrees with respect to the ecliptic plane, okay? Let's draw a picture of that since I don't have my globes with me today. So here's Earth, and here's the sun, okay? And here's the ecliptic plane. The ecliptic plane is the Earth-Sun line. The orbit of the moon, let me use blue. The orbit of the moon is inclined. Now, I exaggerated the angle a little bit, but this angle here is inclined by about 5 degrees with respect to the ecliptic plane. So as Earth orbits the sun, the moon is plunging up north of the ecliptic plane, and then it can sink back down south of the ecliptic plane. Every time the moon crosses the plane of the ecliptic, we refer to that as a node. A node is when the moon crosses the plane of the ecliptic. Let's take that down as well. Moon crosses ecliptic plane. If the moon's orbit was not inclined by 5 degrees with respect to the plane of the ecliptic, you would actually get an eclipse every time there was a new moon and every time there's a full moon. Perhaps I could demonstrate that using some little marble spheres, okay? This isn't great because I prefer to have my globes. But if the moon's orbit, if you guys are the sun, okay, every time, if the moon did orbit in the ecliptic plane, it would sort of do this. And every time you went to new moon, boop, you get an eclipse. And every time we went into full moon, sorry, then you'd have a lunar eclipse. If the moon's orbit is inclined, 5 degrees doesn't sound like much, but you've got this huge baseline, this huge 1 AU distance between Earth and the moon. So 5 degrees above the ecliptic plane could put you well north of the ecliptic plane, or it can put you well south of the ecliptic plane. All right, I'm sucking with the marbles here. It's better when I do this in person. Why don't we look at the book's diagram? They actually have a pretty good diagram in the book to try to explain eclipses. What the artist does is they imagine the ecliptic plane as a sheet of water. And you can see here the moon plunging in and out of the plane of the ecliptic as the moon plunges in and out of the plane of water. Now, all of this is 3D and all of this is rotating in real time. So there are sometimes certain times of the year where if this is the Earth's, if this is the Earth-Sun line here, you can see here at new moon, the moon is actually still in new phase because it's on a kind of vertical alignment with Earth and the sun, but it's below the ecliptic plane. So you don't have an eclipse because the moon is still showing its dark side to Earth. This side that's facing Earth is the dark side of the moon, but it's below the ecliptic plane, so it will not block the disk of the sun. Here, that's the full moon. It's north of the ecliptic plane. So even though you see the illuminated side of the moon at night, you're not getting an eclipse. As the moon continues to slide around in its orbit, it will change its orientation of its orbit relative to the Earth-Sun line. And there are certain times of the year, usually twice a year, where the moon's phase, new and full, will happen to coincide with a node where the moon is coming up through and crossing the ecliptic plane. And those are called eclipse seasons. And there are actually 2 eclipse seasons every year, times where the moon's phase is very close to the moon's node. This is going to be the subject of our lab today, so we should probably learn this stuff. Let's start off doing this as a set of simple notes. I'm erasing this. Did everyone get that? Okay. There are 2 conditions. Sorry. For an eclipse. The first condition is that the phase of the moon must be either new or full. A new moon gives us a solar eclipse. A full moon gives us a lunar eclipse. It's about what is being eclipsed. And the second condition is that the moon must be at a node. And as I mentioned a moment ago, a node is when the moon crosses the ecliptic plane. To understand why we get 6 types of eclipses, we have to understand that there are 2 types of shadow that an opaque body will cast on a screen. The 2 types of shadow are called the umbra, which is total or complete shadow. And then there's something called a penumbra, which is a partial shadow. And I'll show you a diagram once you have that written down into your notes. Okay, let's look at a picture here. Here you can see the sun, an extended body, the Earth, an extended body, and we imagine a screen in space. As seen from Earth, Well, the sun is what's called an isotropic emitter. And what isotropic emitter means is that it means that every single point on the sun radiates light in all directions. So consider the little orange dot that I just drew. That dot gives off so much light, and it gives light in every possible direction that you could possibly draw a ray from. In fact, every dot on the surface of the sun is isotropically emitting in all directions. That means you can pretty much find a ray from any point of the sun that you want to anywhere else you want, but there are limits. For instance, if I picked a point at the top of the sun, I could draw in this ray, which just glances the top of the Earth. Any ray that goes at a lower angle would be blocked by Earth. Any ray at a slightly higher angle would actually pass through and shine over here. But rays from the bottom of the sun would not hit this circle. So if you are here in the penumbra, you cannot see any part of the sun because all rays of light are blocked by Earth. But, sorry, in the umbra. In the penumbra, you do get some sunlight from the sun. Out here, you get all the rays from the sun, both the bottom and the top can hit you. Here's a thought question for the class. Imagine that you were a bumblebee and you were floating around inside the penumbra, and then you looked back towards the sun. Can you tell me what the sun would look like from the penumbra, from right there at that point? That's an interesting geometry exercise. If you're a bumblebee where the little orange dot is and you look back towards the sun, what would the sun look like from the penumbra?
Like an arc? Like
Who said that?
Mateo.
Sorry, I don't know who you are.
Mateo?
Oh, Mateo. Mateo,
Yeah.
you said an arc?
Yes. I don't know. 'Cause
You're
I'm trying to
kind of
think
right. The word I would have preferred, Mateo, is crescent, but you're not wrong. You would see from here, you would see like a crescent sun that looked like that, right?
Yeah.
Yeah, because you'd be able to, and so I think that's what you meant too.
Yeah,
So-
because like the Earth is blocking.
Right,
the
so the Earth is over
sun.
here blocking some, very good. So you had absolutely the right idea. You would see a sort of crescent or a fingernail sun that looks something like that. Okay, cool. Great, so there are 6 types of eclipses. Let's get them down in our notes and then I'll show you some fun pictures. There are 6 types of eclipse. There are 3 lunar eclipses, and there are 3 solar eclipses. Maybe I'll grab a ruler and make a little table out of it. The types of lunar eclipses are called a penumbral lunar eclipse, a partial lunar eclipse, and a total lunar eclipse. For solar eclipses, we have partial, we have total, and then we have a special annular eclipse, which we've already done a homework problem on. That's an A. So the type of lunar eclipse that happens all the time, but you don't actually notice it's happening, is called a penumbral eclipse. And a penumbral eclipse happens in this configuration, where the moon is either partially or completely in the penumbra. Because sunlight can still strike the moon's surface and hit back to you, the moon dims in its intensity, but it doesn't really obviously go through any eclipse, unless you're spending a lot of time staring at the moon. During a penumbral lunar eclipse, over the course of 6 to 8 hours, the moon will slightly dim in intensity, and then it will get brighter again. Most people do not spend 6 hours staring at the moon. They usually, I mean, if you did, you might be a crazy person, right? Or an astronomer. You normally look at the moon when you're running into Cumbies from your car, and you kind of look up and say, oh, there's the moon, right? So if it was in the middle of a penumbral lunar eclipse, and it happens all the time, you'd still see the moon, and you wouldn't have any good reference to realize that it was darker than usual. So you might miss a penumbral lunar eclipse, unless you're paying very close attention.
Why is it that when there's a solar eclipse, you have to wear some like special glasses to be able to see it?
Because because the disk of the sun that you can see, called the photosphere, is extremely bright, has much more light intensity than your eye can handle, and it can really destroy the retinas of your eyes and blind you. Galileo went blind staring at the sun. We'll talk about that in a moment. Matteo. Partial lunar eclipses usually know something is going on because you can see a bite getting taken out of the moon. It's said that Aristotle was able to argue that Earth was a sphere because he could see the shadow of Earth on the moon. He knew that during an eclipse, it was Earth's shadow being projected onto the moon. So you notice partial lunar eclipses. During a total lunar eclipse, it's absolutely amazing. The moon just kind of, instead of turning dark when it goes into the umbra, it turns this evil blood red color, and we call that totality. If you watch it, here's an amazing sort of time-lapse photograph. People go out of their way to get cool photographs like this. At first, you see a bigger and bigger bite getting taken out of the moon, and it seems to go dark. But at totality, you can actually see this red light that's illuminating the disk of the moon. Now, the interesting thing is that if Earth was an airless rock like the moon, you would not get this blood red color during totality. What's happening is that the Earth is surrounded by a thin but significant atmosphere, and the atmosphere works kind of like a lens in that it refracts light from the sun. So light from the sun strikes the atmosphere of Earth, and it bends it or refracts it down. Here we go, striking the atmosphere of Earth. It bends it and refracts it down, shining on the moon. The reason why it does this to red light is the atmosphere of Earth preferentially scatters blue light, pings it off to the side, and preferentially allows red wavelengths of light to pass through the atmosphere. Just think about what a sunset looks like. They look orange or they look red. When the moon is high in the sky, it tends to look kind of yellowish. So all of that light that's leaking through and refracting off the atmosphere of Earth, it's all the red sunlight on a sort of 360-degree ring that's illuminating the moon. If Earth did not have an atmosphere, the moon would be completely dark during a total lunar eclipse. And then again, if the Earth didn't have an atmosphere, we probably wouldn't be standing here breathing and living. For solar eclipses, it's, by the way, I should say this about a lunar eclipse. When there is you are much more likely to see a lunar eclipse than you are to see a solar eclipse. And the reason is pretty obvious. If you're standing here on Earth, anyone on the nighttime side of Earth, more or less, can see a lunar eclipse, right? You've got a 50-50 chance to see every lunar eclipse that happens. Either you happen to be on the nighttime side when it's going down, or you happen to be on the daytime side. Solar eclipses are trickier because the projection of Earth's shadow onto the projection of the moon's shadow onto Earth does not cover the Earth. So if you happen to be in the path of totality here, you will get to enjoy a total solar eclipse. If you're over here in the penumbral shadow, you'll see a partial solar eclipse. But if you're out here, you miss the eclipse altogether. And during the course of an 8-hour eclipse, the path of totality will drift across Earth in a complicated way. It'll depend upon the angle of the moon in its ecliptic orbit, and the spinning of Earth will contribute to that. Usually it makes some kind of cool shape. A nice way to see what eclipses are coming are to look at NASA's eclipse page, and we'll do that together in just a second before class ends. So let's see some pictures here. This is what a partial solar eclipse looks like. Matteo, The disk of the sun that you see here, we'll later study this. This is called the photosphere. The photosphere is the layer of the sun that produces visible light, and it's the disk of the sun that you see on your sky. Even if you're only blocking a part of the sun, or if a small sliver of sunlight shines through, there are so many photons and the intensity of light is so bright coming from the sun that you can go blind just staring at it. Your eye normally has a reaction where it will blink and shut itself down. But if you try to keep your eyes forced open, you can seriously screw up your eyesight. You might think, well, hey, during a total solar eclipse, what do I have to worry about? Well, totality only lasts a few minutes, like 3 minutes. During the phase of totality of a total solar eclipse, you can now see this wispy outer atmosphere of the sun called the corona. Its relationship to coronavirus, corona means crown, right? So we call this the corona of the sun for the same reason they named the coronavirus, because when you look at it under a microscope, coronaviruses have this little crown, which are those spike proteins that are attaching to your cells and invading you. If even a little sliver of sunlight from the photosphere shines through, this light will get totally drowned out. But during totality, you can see the coronal light. The coronal light will not damage your eyes. It just looks cool. But you still need to use special glasses, Matteo, because the disk of the moon, how do I do this? The disk of the moon is like sliding across the sun, right? So just before totality, sunlight is coming through and it slides across and then it slides out again. And you've only got a couple of minutes. And if your eyes are adjusted to the darkness and then suddenly the photosphere peeks out, you can actually mess up your eyes probably more during a total solar eclipse than during a partial solar eclipse, because your eyes will have a hard time seeing the disk. But if you're kind of used to the darkness and your pupils are dilated, you can really get a zap. Of course, if you should happen to have a total solar eclipse within 8 days of apogee, when the moon is farthest away in its orbit, that's when the angular size of the moon will shrink a little bit. And that's when you can get a very special type of an eclipse called an annular eclipse. A nice thing to do if you want to know when eclipses are coming is to check out NASA's eclipse page. And they'll list all the eclipses that are coming, solar and lunar, from now until whenever. Let's see here. We had one recently. This is 2022 now. So we'll go to this bracket, okay? And it looks like, okay. It looks like in May of this year, we will have a total lunar eclipse. And that's just after our class ends. And it looks like it will be visible from the Americas. If we click on this, we should be able to see the universal time. So what you can see here is during an eclipse, the moon is sliding across the umbra and penumbra of Earth. P1 is the moment where it starts to undergo the penumbral lunar eclipse. And U1 is first contact to the umbral eclipse when we start to see a bite getting taken out of the sun. So it looks like.
Oh, I'm sorry.
No, please contribute.
No, I just said that I don't like when they tell us we're going to see an eclipse, because last time when eclipse happened, it just like went through a portion of the United States, so I wasn't even able to see it. So I don't know when they said, oh, an eclipse is coming, but not everyone's going to.
Well, there's a couple of things going on. I have had more of my fair share of getting all my friends up at 6 a.m. to see this gnarly solar eclipse and have drag their sleepy asses out of bed only to have clouds be in the sky and them to all look at me and be like, really, Brendan, that's what we got up for, well, the eclipse is right back there. The other thing is eclipses don't always happen at convenient times. The last one that we had was last year, and it was a solar eclipse that was happening before the sun rose, but we were going to get the one that you're talking about. We had like 45 minutes of it, or maybe 40 minutes of it, but you had to get up at like 5:30 a.m. and it was cloudy that day. So I got 2 of my friends up. We went to the roof of a parking garage in the jewelry district. We happened to have a sight line. You had to be able to see your eastern horizon, which was really tough to do. You'd have to get high. Oh, that's fine, Priscilla. Watch the video for the lab later, okay? And I actually did get to see about, I wonder if I could find any pictures of that. I had some pictures of the eclipse with Vladimir. what did I do with those? I wonder if I could share any of those.
I'm sorry, did you say you were with Putin?
No, sorry. One of my students last year, he is a
Oh.
Russian guy. His name is Vladimir, not Vladimir
Okay.
Putin, another a different Vladimir. He was doing a science project with me. So I was like, hey, Vladimir, there's an eclipse tomorrow. Have you ever seen one? He said, no. I was like, all right, you got to get up with me at 5:30 a.m. Or actually it was 5:15. And we went out there and we saw it. I have some pictures from that, but I wonder what I would have done with those. Astro. I should have thought to prepare those. I bet I could find them before our lab is over. I'll look during our little tea break, okay? Hey, I'm probably out of time for our lecture here because Priscilla had to go. I would like to do one last thing before we go, and my cat is scratching things, so he's hungry. I better feed him. One last thing that I'd like to do before we left is, just like there's 2 periods of the moon, there are 2 planetary periods. And we actually used this in our homeworks last time, but I wanted to get it into your notes as well. Actually, no, maybe I did. Did I put into your notes the difference between a synodic planetary period and a sidereal planetary period? I think I did that in your homeworks. You know what?
Yes.
Better idea. Let's just save this to next time. I want you guys to write this down and remind me that next time, before we do the history of astronomy, I want to have a quick lecture on, or a quick discussion of planetary periods and a little bit more on timekeeping. All right. And then we'll do the history of astronomy. We'll do a little history lesson. All right. Okay, class. The lab today is called Eclipse Predictions. Once again, all you're going to need are pages 5 and 6 from your lab page. Okay. So I handed that out earlier. I need to update for sections 1 and 2. This is the old eclipse prediction. This is the bad one. And I should have put up a new one for you guys. It's in the chat log, or you can request it again. Why don't we I'll change this during break. Why don't we take a 5 to 10 minute tea break, and then we'll come back and we'll start our lab. Does that sound good? So it's currently 1:05. We'll start at 1:15. Sound like a plan? See you then. Hey, for those of you who are printing out today's lab, I realized that on the Eclipse Prediction Improved lab, which I have here, the pages we need are this one. This is 4-4, and we need 4-5. So I'm going to hit print, and I'm going to choose pages custom 4-5 and hit print there. See if that works for you guys. I'll see you guys in a few minutes, okay? Okay, Astronomy 1010, welcome to Lab 3. Today we're going to do a lab on eclipse prediction. It's fun, it's easy, doesn't take very long. We're basically going to be playing Where's Waldo for eclipses. So what we're going to do is we're going to use the rules that we learned during our class today to try to find 4 eclipses, 2 lunar and 2 solar, that are happening in the year 1999. Now, a lot of the data that they have in this lab handout will be helpful here, but all we really need to do our eclipse, because I can walk you through the rest, is we need our 1999 eclipse data, which is 4-4, and we need our data sheet, which is going to have spaces for our 1-2 solar eclipses and 1-2 lunar eclipses, and we're going to hunt them down. Can you guys remind us of the 2 rules, the 2 conditions for an eclipse?
It either has to be full, new, or what's the other one? Full?
Or full.
New or full, right?
Yeah, and the other one was, sorry, I'm trying to remember without looking at my notes.
The
Yeah,
moon must be in a node.
The moon must be at a node where it crosses the ecliptic plane, okay? So why don't we do a little thing here? Do you guys see these little spaces that are in your handout? Above new moon, why don't you write the word solar to remind, right here in that little gap, write solar to remind yourself that new moons produce a solar eclipse, and under full moon, we'll write lunar, okay? Okay, today we're going to learn that there is some additional issues at stake. Boy, it would really be great if I had those darned globes here. I'm seeing that now. If you think about it, maybe I could use the drawing from our textbook to help here. Once I share screen to the iPhone, I don't want to unshare it because that tends to create bugs. Let's go over to our Eclipse slideshow. And I want us to go back to that picture of the moon orbiting Earth sliding in and out of the ecliptic plane. In this picture, it shows 4 different times of the year. Times where new and full moon happen to take place pretty much at a node. And these are times where the nodes are happening at first quarter and third quarter moon. In actuality, each month, the time of the moon and the time of the node is a little bit random. It could happen, and perhaps here I could just try to do a 3D drawing of this. That might be the best way to go about it. So let's draw the sun we'll put the sun over here, okay? And then let's put the Earth in blue over here. And, line them up. And we'll use a blue line to represent the ecliptic plane, maybe a light blue line, okay? So here's the plane of the ecliptic. Now, there are 2 alignments happening in a sort of 3-dimensional sense. If you think of this as a 3-dimensional sort of situation, the ecliptic plane is actually like a sheet, right? And I'm only going to be so good at, actually, maybe I could use straight line. Ooh. Straight lines for this sheet, okay? So here's the sort of plane of the ecliptic. I normally do this in our lab rooms with some globes, so it helps to see it 3D. Let's use sort of yellow for the moon here, okay? So let's draw a little moon, and then let me grab hold of it, and let's think of what's going on. The moon is sliding up and down, in and out of the plane of the ecliptic, right? And anytime it crosses the ecliptic plane, when it cuts through this sheet, that's going to be a node. There's also an exact time of new moon or full moon, and the exact time is when it's lined up. It's not always going to be exactly on this perfect ecliptic line, but I now want you guys to imagine another plane. This is going to be a little hard to draw. This one is a plane which intersects the blue plane. And there's no good name for it. It's like perpendicular to the ecliptic, or if there is some old-timey astronomy name, I don't know what it is. It's kind of this vertical plane that cuts through the sun and the Earth. And when the moon is sort of in an alignment vertically, it could be slightly above the ecliptic plane or slightly below the ecliptic plane. Here, this is almost going to be impossible to do without some kind of a 3-dimensional aid. Okay, so let's get back to the marbles. That's all I've got. Like I said, my car is still at CCRI. Here's the Earth. Your camera is the sun. And we're coming up and down north and south of the ecliptic plane, cutting through as a node. The exact time of new moon is considered when it's on a sort of vertical alignment between Earth and the sun. In other words, if you guys are the sun and this is the Earth, new moon happens when I'm either above the ecliptic plane or below the ecliptic plane, but I have to be on this kind of vertical alignment, this up-down alignment, okay? I can slide up into new moon, down into new moon. That's an ascending node when you're going up. At other times of the year, it might be that I'm on a descending node. I'm descending through the ecliptic plane, but that I end up slightly below the plane of the ecliptic, but I'm still on this vertical alignment here, okay? Now let's look at our data sheet and try to understand what's going on. I'm also going to want a blank piece of paper to walk you through our eclipse conditions. Maybe I can use this yellow legal pad here. Let's see if I can't connect to our phone here. Share screen. Boom. Screen mirroring very soon. And everyone see this okay? All right. Let's begin, as we always do, with our name. Section is AS1010. You're either in 001 if you're in the Monday lab, the Wednesday lab is 002, and the night class is 101. So put whatever your section is. Also remember, it's a really great idea to write the lab number. That way we can all keep track. This is lab 3. Slide over with me now to your eclipse data from 1999. Notice that for each month, there is an exact date and time of the new moon. That's when it's on the vertical sort of alignment. There's also an exact date and time of the node, and that's when it sort of crosses the ecliptic plane. So there's a node there and there's a node there. The time of the node and the time of new moon are never going to be the exact same microsecond in time. But you can imagine that if the time of new moon is only different from the node by about 5 minutes, there will still be enough of an alignment to create some type of an eclipse. How close can the moon and the node be and still create an eclipse? Now we're going to get into some more nuanced and nitty-gritty data. So let's start with our first condition. Our first condition is going to be 28 hours, okay? And this applies for both lunar and solar eclipses. If the time of the moon is less than 28 hours of the time of the node, then pow, you get some type of an eclipse. So 28 hours is going to be our reference mark. The game that we're going to play is going to be very similar to 28 blackjack. We are going to hunt for 2 lunar eclipses and 2 solar eclipses. Don't forget, you should have written solar above new moon, lunar above full moon. We'll take them one at a time. And we're going to compare the time of the the new moon to both the ascending and descending nodes for each month. If the node and the moon are less than 28 hours apart, then we will have found an eclipse. Because we're going to be using a 24-hour military style clock, it might be good for those of you who are not accustomed to thinking about this to actually label the numbers 0 through 24, which might actually help us count in a visual sense. And you can do that right down here. You can just do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I've discovered through long experience that this can help to just kind of put the numbers 0 through 24 on a line here will help us when we have to count hours, because this can get confusing. Another great idea, have your Casio calculator out and handy so that we can add and subtract times, okay? Okay, so we've got a number of other questions to answer, but I'm going to walk you through the discovery of one of the solar eclipses, and then I'm going to see if you guys have any skill at this, okay? Let's start by not worrying about the lunar eclipses. Let's just focus on the solar eclipses for now. Our goal is to compare the time of the new moon to both the ascending node and to the descending node, because an eclipse can happen if the new moon is less than 28 hours from either ascending or descending node. It can go either way. What we're going to do first is we're going to look for the date, and we're going to check to see if the time or if the date of the new moon is 2 days or less than either of the nodes. Now, let me explain this 2-day thing. Rather than just trying to count hours right off the bat, we can speed things up by considering 2 days for the following reason. Let's imagine that we transition a moon and a node. And I want us to imagine going a 24-hour day from, say, Monday to Tuesday to Wednesday. Just hear me out for a second and humor me. So let's say this is a Monday, this is a Tuesday, and this is a Wednesday. We know that each day has a 24-hour clock associated with it. So there are 24 hours from midnight to midnight on Monday, Tuesday, and Wednesday. Our criteria is 28 hours. If you think about it, it might be possible to have the time of the new moon be at 2300 hours, right? And the time of the node could happen on Wednesday at 0100 hours. And if the node and the moon were separated by this length of time, they would be, first there's the Tuesday 24-hour, 24 hours, 25 hours, 26 hours apart. And thus it's possible to have, although unlikely, it's possible to have the moon and the node be 2 days apart and still be less than 28 hours between each other. Did that make sense? So what I think we're going to do is first we're going to look for days where they're 2 days or less apart. And if they are, we're going to carefully count the hours between moon and node. Okay? Let's begin. Our first date is Jan 17th. To make this thing a little bit easier for counting, for now, we're going to round up our time. So instead of 1546, let's just call it 16 o'clock. That way we don't have to worry about counting minutes too, which is going to be unnecessarily burdensome. There was a node on January 5th. Are those 2 days apart? No. So there's no eclipse there. January 19th is 2 days apart from the 17th. There could be an eclipse. We have to count hours now. Let me see if I can do this sideways. I wonder if that would be a little gentler on this system here. Let's see if I can go sideways here. If I shake this thing correctly, I do not have the portrait block on. So I should be able.
Are you trying to count from 16 hours on January 17th to, let's say, 14 hours on January 19th?
Hold on, wait. Okay, fine. My flipping the screen isn't working and you're getting impatient. Let's start with this fact. Jan 17th comes before Jan 19th. How many hours are left in Jan 17th?
4.
I'm
sorry, 6.
8.
8. Because 4 hours gets you to 20 o'clock and another 4 gets you to, right.
24.
So I like to use my calculator for this. So we're starting off with 8 hours, right? Okay, but then from Jan 17th to Jan 19th, Jan 18th is in between. How many hours is that?
24.
So now we do 8 plus 24. Boom, you're busted. This is just like the game 21 Blackjack. If you go over 21, you're busted. Here, it's 28 Blackjack. 32, we're busted. Doesn't even matter how many hours into the 19th we are. So no eclipse there. Let's go down to the next one. February 16th, it says 639. I'm just going to round it to 700 hours. Oh my gosh, look at this. Here we're seeing the issue that the synodic period of the moon is 29.5 days. So if you have a node at February 1st, you can also have a node on February 28th, right? Or sorry, the nodes go on the sidereal period, 27 days. This gets confusing. The nodes are the true 360-degree orbit, so they're not about seeing phases. So they follow the 27-day period. Anyways, we've got 2 ascending nodes and 1 descending node. Feb 16, Feb 1, no dice. Feb 16, Feb 28, not 2 days apart. Feb 15 is 1 day apart, so we should count the hours. Let's round Feb 15 to 2,200 hours because that's what it's closest to. If the 15th comes before the 16th, we have to start counting the hours here. 22 o'clock, how many hours are left in Feb 15?
2.
2. So we'll start by putting that in our calculator. 2 hours plus. How many hours into Feb 16 are we?
7.
2 plus 7 is 9. That is less than 28 hours. Bing, bing, bing. We have discovered a solar eclipse. Now, you might wonder, what is the real time of the eclipse? Is it the time of the node or is it the time of the new moon? It turns out to be the time of the new moon. That's when the moon is going to be on its most vertical alignment, and that's when you're going to eclipse. That's when the disk is going to block the maximum amount of sunlight. So let's write down Feb 16th. This time we'll go back to 639 and we'll write that all right here.
Quick question.
Yeah.
So how come we're counting the hours already in the day instead of the duration in between the nodes?
We are counting the duration in between, but we're counting
the hours into February 6th and what's remaining for February 15th instead of what's in between.
Oh wait, you just fed February.
We started on February 15th. That's
No, I know. I'm saying, like, why didn't we do the same thing that we just did for the first one too, to try and?
Because in the first case, the moon came earlier than the node. In this case, the moon was on the 17th and the node was later on the 19th. So we had to start counting here at the earlier date.
So that's just counting up.
Yeah, we're counting from the earliest date to the latest date, forward in time. Are we satisfied?
Yeah, I was just making sure I got the durations right.
Yep, and these are good questions. This is wicked confusing when you start it off. Trust me, everyone goes through this. Okay, so we got our first solar eclipse, Feb 16th, 639. Let's all write that down. Now I'm going to walk you through how to do the other questions. Local date and time. Eastern Standard Time, traditionally, Eastern Standard Time is the time at Greenwich, England, Universal Time, minus 5 hours, okay? But Eastern Standard Time runs from, let's see, from October something to April something. I forget if it's like the first Sunday or the last Sunday in October and April. Basically, that means Eastern Standard Time is during the winter months, if you want to keep it simple. During the summer months, we use Eastern Daylight Time. We have to observe daylight savings time, and that's Universal Time minus 4 hours. That's from April through October, which we can think of as the summertime. In our case, the time of the eclipse was February during the winter. That makes us Eastern Standard Time, and we're going to subtract 5 hours to get the local time of the eclipse. Now, they suggest we use AM or PM, but I think that's kind of silly. It spoils the whole point of using a 24-hour clock. So we're just going to do Feb 16, and we're going to subtract 5 hours to get 139. That will be the Rhode Island local time at which the eclipse is at the midpoint. So this eclipse in 1999 was happening at 1 in the morning. Okay, is it central or partial? Here are the rules for central versus partial. I should try to use the tape here so I'm not jiggling about. Sorry, guys, there's a lot of stuff on my desk. Okay.
Wait, so the solar eclipse was happening in England or like wherever the England line is?
That's the wrong way to think about it. The solar eclipse was happening. The question is, who can see it? Can England see it? Can we see it? The answer is probably
winter can see it.
Huh?
Whoever's in winter can see it.
No, it's not that simple. For a solar eclipse, in order to have the possibility of seeing it, it would at least have to be during the daytime. Given that the fact was mid-eclipse for Rhode Island at 1:39 a.m., there is absolutely no chance a Rhode Islander could have seen this solar eclipse. Now, in February at 6:39 a.m., you could probably see the sun, maybe.
No, I don't think so, because that's winter and it's up there.
No, it's only if it were 4 hours. That'd be for the summer. It'd be different.
It doesn't matter whether it's 4 hours or 5 hours. It matters about the path of the eclipse. First of all, you have to be able to see the sun to see the solar eclipse. So it has to be during the day. But the reason why they say possibly visible is even if you are up during the day, you might not be in the path of totality. I don't want to lose my iPhone connection here, but I would like to show you a picture from NASA's eclipse page of what this looks like.
Totality for it being past midnight.
I'm sorry.
Or we can't determine the totality of it past a certain point unless we subtract the amount of hours if it's on.
That's not the correct way to say that.
5 or 4 hours.
Calculating the path of totality is outside your pay grade. It's very tricky to do. And as a demonstration of why, I'd have to call up this map.
Totality is a path.
Yeah, totality is a path. You were kind of breaking up there, so it's hard to. I need this to.
Could you explain that for me?
I
have no idea how that works.
Yeah. So first of all, to see a solar eclipse, it's got to be daytime. Okay. And the path of totality across Earth is quite complicated. That's over the pay grade of this lab. You've got to actually calculate the fact that totality will move across a spinning Earth from north to south, and it will cut through even something like the United States in a complicated way. Now, if we scroll down here, I don't know how much of this they do, so let's clear all drawings. Let me go back. One of these will show a map of the United States. I can't remember which one does it. Maybe it's this one. That's not good either. The problem is I don't think I should explain that too, because it's going to take, first of all, I'm having trouble getting the damn picture that I want. And second of all, I'm doing this through my phone, which is extremely irritating. If I disconnect from the phone, I might have to reboot my phone, and that's going to take even more time. I'm afraid it's a little annoying here. This has the map of the US, but it's not loading for some reason. You're just going to have to trust me that calculating the path of, you know what? Fuck this. I can just Google this. So solar eclipse path of totality, and it'll show me some picture of the path of totality here. Yeah, here's a great picture of a solar eclipse. This is a 2024 solar. This is the next solar eclipse that Rhode Islanders will be close to. Give me the goddamn picture, you bastard. Everything is just failing for me today. Or here was a recent solar eclipse. I think because I'm trying to live stream this, we're running into some trouble here. Come on. Oh, not this again. Yeah, this is an example of what the path of totality looked like for the last solar eclipse, the one that happened about a year ago or so. You might be able to see a partial eclipse from these states. Oops, that's not what I wanted to do. Thank you very much. But to see totality, you actually had to be in this complicated path. So calculating that trajectory is a little bit over the pay grade of this lab. Let's not worry about it. Our eclipses can either be central or they can be, well, for a solar eclipse, it's central. For a lunar eclipse,
I can't see the phone. We're seeing through your.
Damn it! I went and lost the bloody thing, anyways. Thank you. It's a little tricky to kind of juggle screen, phone, and me, so I'm doing the best I can, guys. Just bear with me. Labs aren't easy to do over Zoom. Okay. Central or umbral, so this is for solar eclipses, and this is for lunar eclipses. This is when the two things are lined up with each other, right? So central just basically means the two disks are lined up. They could either be total or annular, but they're centrally located. Then there's either what we would call for a solar eclipse, partial, or for a lunar eclipse, we would call penumbral. If the time of the moon and the eclipse are from 0 to 20 hours apart, then it'll be central or umbral if it's lunar. If the time of the moon and the time of the node are 20 to 28 hours apart, then they'll be partial or penumbral. Remember that when we counted hours from 22 o'clock Feb 15 to 7 o'clock Feb 16, that was a 9-hour period, which makes our solar eclipse a central solar eclipse. The notes will walk you through all of this as well, but they're confusing.
I'm sorry, can you repeat that? I got lost there.
Yeah, sure. I didn't do a wonderful job there. Okay, first of all, let me explain why we have to differentiate. Let's just focus on solar eclipses. Let's talk about the difference between central versus partial eclipses. In a central eclipse, the fan is blowing this around here. This is the disk of the sun. And let's say, quarter would be helpful here. Something. And let's say this is the disk of the moon. A central eclipse means the center of the disk of the moon will align with the center of the disk of the sun. Now, it could be annular, like you see here, or it could be a total eclipse where it completely blocks the sun, but those are central eclipses. Central solar eclipses happen when there's a close proximity between the time of the node and the time of the moon, less than 20 hours apart. If the time of the node and the time of the moon are between 20 and 28 hours, that's when you get a partial eclipse, because you don't actually get to cover the full disk of the sun. In that case, the disk of the moon and the disk of the sun are not centrally aligned. And that's where, instead of seeing a totality or a total solar eclipse, the disk of the moon will only block a part and you will see the sun as a fingernail, right? So basically, we're trying to determine and predict in advance, will this be a total solar eclipse or an annular eclipse, or will it be a partial? Since there were only 9 hours, February 15th happened at 22 o'clock, that's the node. 2 hours plus 7 hours means the time of the node and the time of the moon were only 9 hours apart. And if they're less than 20 hours apart, that makes them central. Did that sound better this time, or was it still confusing, Matteo?
No, I got it now.
Okay, sorry. I'm trying to figure out how to make this confusing stuff less confusing. It's not that easy. Okay, question 4. Was your eclipse happening north or south of the ecliptic plane? There's only one way I know how to do this. Let's draw a circle to represent Earth. Let's draw a circle to represent the sun. And let's put a dashed line in between them. The dashed line will represent the ecliptic. Okay, let's take a look at our eclipse again. Our eclipse was transpiring during a descending node, meaning during the eclipse, the moon's trajectory was pushing down through the plane of the ecliptic. I'm going to draw the path of the moon as a downward pointing arrow because it's descending through the ecliptic plane. I know that the time of the node was right there when the moon crosses the ecliptic plane, and that was on February 15th. The question is, did the eclipse, the total eclipse, happen before or after the node? Our eclipse happened on February 16th at 7 o'clock. So if the moon's moving down and Feb 16 is here, Feb 15 is at the node and Feb 16 is here, then our eclipse had to be south of the ecliptic plane. This is north and this is south of the ecliptic plane. So because it was a descending node, and because the time of the moon came after the node, that means it was south. You kind of have to do that picture every time to figure that out. Was it total or was it annular? The condition for total versus annular eclipse has to do with the time of apogee. You will remember that apogee is when the moon is farthest from the Earth in its orbit. So that would be apogee. It's kind of like aphelion. For a total eclipse, if the time of the moon happens less than 8 days from apogee, the eclipse will be a total eclipse. If your central eclipse is annular, that's if the moon is greater than 8 days from apogee. Our eclipse happens on Feb 16. The date of apogee was February 9th. How many days transpired from Feb 9 to Feb 16?
7.
7. That puts our condition as total. So we write that in. Possibly visible from your location is the easiest. Remember that the solar eclipses are happening during a new moon, and the new moon is up all day. Can you see the sun at 1 a.m.? No. There is no chance you could have seen that solar eclipse. Okay, I know that was a bit janky your first time going through. So for part 6, remember that the new moon is up all day. Remember that the full moon is up all night. Everyone take a little snapshot of these conditions here. All right, let's go back to condition 1. There is another solar eclipse hiding in here. Now, I'm going to grab a glass of iced tea, and I want to see if you guys can find it. Fuck me. Okay, sorry guys. I'm trying to balance this with some tape. What we would need to do is we would need to proceed to the next date, March 17th, and compare it to these two nodes, and then go to April 16th, compare it to those two nodes, and keep comparing to those nodes until you can find one that's less than 28 hours. See if you
I
can
have one
find-
question.
Yep.
Because the node is 709, would you round to 7 or to 8?
I would round to 7, just the closest hour. The
Okay.
truth is, Ethan, the minutes aren't going to really determine this. The number of hours apart will. In
Yeah.
reality, it could come down to a matter of minutes, but I didn't give you one that was that sneaky, okay?
Okay.
So why don't you guys hunt for that other solar eclipse and see if you can find it by the time I get my iced tea. I can, of course, tell you where it is, but that's no fun. Sorry, guys. This is a very chatty lab and it's thirsty business. I'm wondering if any of you could find the other solar eclipse. Anybody?
Is it August 11th?
Very good. August 11th has a date of new moon. There was a new moon on August 11th, but there was also an ascending node on August 11th. If you think about it, they're on the same day, so they have to be less than 24 hours apart. That means you've got to have an eclipse. This one happened around 2 o'clock, and this one happened around 11 o'clock. So if we're using military time, 2 hours comes before 11 hours, right? How many hours apart were they? 11 minus 2 is 9 hours apart. Let's write down August 11th, 1108. Okay, did the August 11th eclipse in 1999 happen during Eastern Standard Time or Eastern Daylight Time?
Eastern Daylight?
It was August, so it took place in summer. To get to our local time, we will subtract 4 hours. That brings us to
708.
Exactly, thank you. Okay, you guys are getting it now. Next question. Was this a central eclipse or a partial eclipse? Do you guys remember how many hours apart they were?
9.
9 is under 20 hours, making it also a central eclipse. A central solar eclipse. Did it happen north or south of the ecliptic plane? Let's go ahead and draw our picture. Down here, I'll draw the Earth and the sun. I use a dashed line to represent the ecliptic. This took place during an ascending node. So this time the orbit of the moon was heading up through the ecliptic plane. Now they both happened on August 11th, but the time of the node was 200 hours military time. Was the time of the moon before or after the eclipse?
After.
1100 hours comes after 200 hours. So by the time the eclipse was in full swing, it was happening north of the ecliptic plane. For total versus annular, it's about whether or not it was more than 8 days from apogee. The time of the moon was August 11th. The date of apogee was August 20th. How many days apart are they?
9.
9 days apart. Greater than 8 days means this was an annular eclipse. Do you think it might be possible to see the sun at 7:08 in August?
Yes.
Then it is possible we would see this eclipse. Whether or not we were, now someone was asking about the path of totality. Whether or not we actually happen to be in the path of totality, as I mentioned, is a little over the pay grade of this lab. That takes some 3D geometry skills to work out. And it takes a little while. You probably have to use a computer simulation to do it. Okay, let's see if we can quickly hunt for our 2 full moons. We're going to play the same game again, but this time we're going to be looking for lunar eclipses in the full moon category. Once again, we will compare them to both ascending and descending node. Jumpin' Jesus, it looks like there were 2 full moons in the month of January. Notice that because the synodic period of the moon is 29.5 days, if you have a month with 31 days, and you have a full moon occurring at the beginning of the month, it's possible to have a second full moon in a month. Do you guys know what they call that when there's a second full moon in the same month?
Isn't it a blue moon?
That's right, it's a blue moon. Now, people say once in a blue moon as if they were rare, but look at the year 1999, and you realize that there are actually 2 blue moons in the year 1999. Now, I don't know how many blue moons we're going to get in 2022, but I happen to have this cool lunar calendar gift. And blue, my whole point is blue moons are somewhat more common than one might think. The full moons here.
Oh, I just remembered. Happy
Little-
New Year.
Say that again?
It's a lunar year. It's Happy New Year today.
Oh, yeah, that's Chinese New Year. That's different. We'll talk about that next class. None of the full moons in the year 2022 happen right at the beginning or ending of a month. So there's actually no blue moons this year. But it is possible to have several blue moons in the same year. They're not quite as rare as you might think. If we do have a blue moon, that requires us to compare not only the time of the moon to the nodes within our own month, but if we think about it, what day comes after January 31st?
February 1st.
And holy crap, there was a node on February 1st, right? That means these could be less than 28 hours apart and we should count them. Okay, first comes January 31st. If that's 16 o'clock, how many hours are left in that day?
8.
So there's about 8 hours there. And then how many hours into February 1st were we?
13.
So 8 plus 13 is 21 hours, and that constitutes less than 28. And that means on January 31st at 16:06, there was going to be a lunar eclipse, or there was, since this is in the past now. Okay, local date and time. Was this Eastern Standard Time or Eastern Daylight Time in January of 1990? Standard Time. So we'll subtract 5 hours to get 11:06. Umbral or penumbral follows the same rules as central or partial. Less than 20 is umbral, greater than 20 is penumbral. How many hours separated these two nodes and moons again? The node and the moon?
21 hours.
So 21 would actually make this penumbral, meaning it probably wouldn't have been that impressive to the average observer. Possibly visible from your location. This is military time 11:06, which is 11 a.m. Can you see the full moon at 11 a.m.?
No.
No, the full moon's up all night. So no way would you have been able to see that penumbral eclipse, even if you were floating around in 1999, which some of you weren't. Okay. Let's see if we can find that second lunar eclipse. Anyone think they can pick it out of a hat here?
July 28th and July 29th.
Bingo. Excellently done. Let's count the hours. There's roughly 12 hours left in that day, plus 2 or 3 into that day. So that's 13 hours at best. That's definitely an eclipse. July 28th at 11:25. Nicely done. And you guys are getting the swing of things now. Was that, sorry about my penmanship, guys. Was that Eastern Daylight Time or Eastern Standard Time?
Daytime.
Yeah, because it's the summer. So we have to subtract. Eastern Daylight Time is 4 hours from the Greenwich, England clock.
So
11
so 728 hours.
Thank you. Okay. Penumbral or umbral is about 20 hours, greater or less. We decided that these things were 12 hours, 13, 14, maybe 15, but regardless, it's under 20. So that would be an umbral lunar eclipse, meaning it was a total lunar eclipse. Is it possible to see the moon at 7:30 a.m. in July, the full moon?
No.
Yeah. I don't think you did.
I just noticed that you didn't put January 31st. Is that a for
Oh.
the first.
Yeah, look, thanks, dude. Oh, I'm sorry. I'm like a little, oh man. Just having a day, guys. I'm sorry. Hey, Mateo, thank you. Mateo, talking, thinking, writing, holding an iPhone, it takes just a little more skill than I seem to have today. So thanks for keeping me on my toes here. So he just thought we should put the date in. I think that's, sorry, can you guys see that, what I did there? All right. Do we have all this information? All right. Before we end here and before you turn things in, that first lunar eclipse, the one that happened on a blue moon, we actually have some NASA footage from the 1999 lunar eclipse that took place during a blue moon. I thought maybe I could share that with you. Here it is. All right, ready? There you have it, guys. Every blue moon, once in a blue moon, you get one of those lunar eclipses. Okay, so please turn in your lunar eclipse sheet. I'm sorry, I know that was a little confusing. Guess what? Astronomy is confusing. Astrophysics is confusing. Reality, nature is confusing. That's why we have to work hard to discover her secrets. But it can be done. Please turn in those labs, and I will see you guys on Wednesday for another fun lecture, and we'll do homework 3. Sound like a plan? Those of you who owe me stuff, Marissa, Ethan, William, you owe me some stuff, but you're going to do it, right?
Mm-hmm.
Okay.
Yeah. Just had a quick question about, did you want us to copy down? You also had like a yellow notepad of some important stuff. Do you want us to submit that or?
No, I think you could have that as your bonus notes for advanced eclipse prediction. And if you ever did want to look back and learn more about eclipse prediction, that'll be a starting point for you. So just turn in that one sheet. Just that'll be easy for everyone. And I like easy. Okay. All right.
Awesome. Thank you.
That's great, Ethan. Okay, so everyone, I'll see you guys next time. Peace out.